Okay, so in our last video, we talked about just the intro to what confidence intervals are. We went over describing a confidence interval. We talked about the different parts that go into a confidence interval and how to interpret both the confidence interval and confidence levels. So I want to do a little bit of review here before we get into actually calculating some confidence intervals today. So this first problem says a manufacturer of flashlights wants to know how well one of their newer styles is selling in a chain of large home improvement stores. They select a simple random sample of 20 stores and record how many flashlights were sold in a 30-day period and construct a 95% confidence interval for the mean number of flashlights sold. If instead of constructing a 95% confidence interval, the flashlight manufacturer constructed a 98% confidence interval, would the 98% interval be wider, narrower, or the same width as the 95% interval? Well, let's remember from our notes what the level changes. So on our formula sheet, we know we have three parts that go into our confidence intervals. We have the statistic, which is what we're gathering from the sample, plus or minus the critical value, that's the number of standard deviations away from the mean we're calculating, times the standard error of the statistic. The margin of error is what determines our width, right? Our statistic, or our point estimate, is our center point, and we're adding and subtracting this margin of error from that value to get our full interval. So the width of that interval depends on two things. Critical value, which remember that is calculated from the confidence level, and then the standard error of the statistic, which is like our standard deviation, which is affected by sample size. So the confidence level is going to affect the critical value. The larger the confidence level, the larger the critical value. Because the larger our confidence level is, the further away from the mean we're looking, right? And a 95% confidence interval means we're looking at the middle 95%. A 98% interval would go out 98% away from the mean, right? The middle 98%. So a 98% would be wider than a 95%. How would the width of the confidence interval change if the flashlight manufacturer took a larger sample? Okay, well, what is sample size effect? Sample size affects variability, right? We learned that in chapter 7. And as I increase sample size, it decreases variability. So how would the width of the confidence interval change? It will become more narrow with a larger sample. The 20 stores in the sample were actually the only stores who provided sales figures from 36 stores that were randomly chosen to be in the sample. Can the manufacturer adjust the confidence interval to take this non-response into account? If so, how? If not, why not? Okay, again, going back into our calculation of what is in a confidence interval. We have the statistic, which is what we gather from the sample. We have the critical value, and we have this standard deviation. Can any of these take bias into account? No. There's no room for bias in here. We cannot take that into account at all. Okay? There is no room for bias. There is no way to take that into account. That margin of error is just there to account for the natural variability that happens with sampling variation. All right, good. Let's try some multiple choice questions. And we're just going to do maybe about 4 or 5 of these. Okay, so the admissions director from Big City University found that this interval, 107.8 to 116.2, is a 95% confidence interval for the mean IQ score of all freshmen. Discuss whether each of the following explanations is correct. A, there is a 95% probability that the interval from 107.8 to 116.2 contains mu. B, there is a 95% chance that the interval 107.8 to 116.2 contains x bar. C, the interval was constructed using a method that produces intervals that capture the true mean in 95% of all samples. D, if we take many samples, about 95% of them will contain the interval 107.8 to 116.2. Or E, the probability that the interval 107.8 to 116.2 captures mu is either 0 or 1, but we don't know which. Okay, so what does that 95% confidence tell us? Remember, that's the confidence we have in the method that we're using to produce the interval. It's not the confidence we have in the specific interval. So A cannot be correct. That is not tied to the specific interval. Same thing here. That is not tied to a specific interval. The probability the interval captures mu is either 0 or 1, but we don't know which. Actually, the probability, that's not going to be true either. We're not going to use that one. However, there is a 95% chance, if I've used this method, that I've created an interval that captures it, right? What's the problem with this one? There's a 95% chance that the interval contains, well, there's a 100% chance that it contains x bar, right? Because that's the point estimate. It's going to be right in the center. Now, if they had said mu, that would have been different, right? So just be very careful when you're reading those problems. All right, good. Let's try now. All right, 21 and 22 refer to the following setting. A researcher plans to use a random sample of families to estimate the mean monthly family income for a large population. The researcher is deciding between a 95% confidence level and a 99% confidence level. Compared to a 95% confidence interval, a 99% confidence interval will be, okay, let's think about this. We talked about this earlier. If I increase my confidence level, what does it do to my interval? It makes it wider, right? And that should be the only thing it affects, right? All right, so since I know it's wider, I can not even read the ones that say narrower. All right, so B says wider and will involve a smaller risk of being incorrect. D, wider and would involve a larger risk of being incorrect. And E, wider and would have the same risk of being incorrect. Okay, well, if it's wider, I should have a better chance of capturing it, correct? So I should have a smaller risk of being incorrect. All right, number 22. The researcher is deciding between a sample size of 500 or 1,000. Compared to using a sample size of 500, a 95% confidence interval based on a sample size of 1,000 will be, what happens when I increase sample size? When I increase sample size, it reduces variability, right? So if it reduces variability, it should make my interval narrower. So I'm going to ignore the wider ones, right? If it's narrower, how would my risk change? Well, if it's narrower, I have a less likely a chance if I change my confidence. But did I change my confidence here? I did not. So the risk is tied into the confidence. Up here, we were talking about changing confidence, which changed the risk. Here, all I did was change sample size, which changed the width of the interval, but is it changing our risk? No. So it's narrower and it'll have the same risk, because if this and this both have the same confidence level, that's where our risk is. Okay? 95% of the time, either method would produce an interval that captures the truth. All right, two more. In a poll, some people refused to answer questions. Some people without telephones cannot be in a sample, and some people never answer the phone in several calls. Which of these possible sources of bias is included in the plus or minus 2% margin of error announced for the poll? Can we account for any of these? No, because they're all biases. Remember we talked about the end of the lesson last time? Bias can't be accounted for here at all. So none of these could be accounted for in an interval. All right, last multiple choice, then we'll try a few more practice. You have measured the systolic blood pressure of a simple random sample of 25 company employees. A 95% confidence interval for the mean systolic blood pressure for the employees of this company is 122 to 138. Which of the following statements is true? A, 95% of the sample employees have a systolic blood pressure between 122 and 138. Are we firm with these two as our boundaries? No, that 95% is not tied to specific boundaries. 95% of the population of employees have a systolic blood pressure. Again, it doesn't matter if it's sample or population. That percent is not tied to the specific interval. C, if the procedure were repeated many times, 95% of the resulting confidence intervals would contain the population mean systolic blood pressure. That's the definition of a confidence interval, isn't it? If I were to do this many times, this is how confident I am that this method would produce an interval capturing the truth. Both of these, again, going back to trying to tie the percentage to an actual interval, and that's not true. All right. Suppose you know that the distribution of finishing times for a certain crossword puzzle has a mean of 25 minutes and a standard deviation of 8 minutes and is moderately skewed left. You take a simple random sample of 45 finish times from this distribution and calculate the mean finish time x bar. Describe the shape, center, and spread of the sampling distribution of x bar. All right, how do I know this is going to be normal-like? Well, I'm dealing with means, and I have a large sample size, right? And if I have a large sample size, the central limit theorem lets me know, hey, this is going to be normal-like. So normal-like because central limit theorem. All right, the mean. The mean of this distribution should be the mean of all the x bars, which should be the actual true mean, which should be then 25. And the standard deviation is going to be the population standard deviation over the square root of n. So 8 divided by the square root of 45. So we grab our calculators and say 8 divided by the square root of 45. We get about 1.1926. Find a number k such that 95% of the values in the sampling distribution will lie within k minutes of the mean. Okay, if we're looking at the middle, 95%. Remember, that's 2 standard deviations on either side, right? And we talked before, if I'm looking at the middle 95%, if I'm looking at 2 standard deviations on either side, that means I just need to take that standard deviation and go 2 on the right side and 2 on the left side. So the k that I would add to both sides would be 1.1926 times 2, right? So that would be 2.38. Well, 52 if I doubled it right. Okay. And that actual interval I could find by subtracting that from 25 and then adding it to 25. If you take repeated samples of size 45 from this population, what proportion of the time will the mean you find plus or minus this value contain the number 25? Well, how confident am I in this? 95, right? So if I'm 95% confident, that means 95% of the resulting samples that I gather should give me values that give me an interval that captures the truth. All right, number 2 says the confidence level is sometimes called the capture rate. Explain why this is an appropriate term. What's the whole purpose of the confidence interval? The whole purpose of a confidence interval is to capture the true mean or true proportion. And so the confidence level is called the capture rate because it's the rate at which we're capturing the parameter. All right, number 3. An insect ecologist reports 95% confidence interval for the mean length of full-grown aquatic larvae from the phantom midge. I don't know Greek. I don't know Greek either, but I don't know Latin, so I don't know the actual term here. To be 6.9 to 8.5 millimeters based on a sample of 9 individual larvae. What are the point estimate and the margin of error associated with this confidence interval? Okay, so if we have a confidence interval, where should the point estimate be? Where should the mean from the sample be in that range? Well, it should be smack dab in the center, correct? So we can average these two numbers together, add them together, divide by 2, or you could just look at it and figure out exactly what the center would be. But the point estimate, or the average length here, right in the center, would be 7.7 millimeters. Margin of error. Well, the margin of error is what I'm adding and subtracting from 7.7 to get these two numbers, right? So if I say 7.7 minus 6.9, that gives me 0.8. So the margin of error here is 0.8 millimeters. So if I were to write this out, I could say, okay, 7.7 plus or minus 0.8. And when you're writing an interval, either one of these is appropriate. This is nice because we like to talk about a whole interval. Here it is. This is nice because it shows separately what I got from my sample and then how large my margin of error was. Part B says, if the ecologist had reported a 99% confidence interval instead of a 95% interval, how would it have been different? Explain. Well, what does the confidence change? The more confident I am, the more sure I am that I'm going to capture the truth, right? So the less risky it is for me. I'm more confident. And if I'm more confident, it's going to increase the width of the interval, isn't it? If I'm looking at the middle 99% instead of 95, my interval would be wider. And I would be more confident in my answer. The ecologist was unhappy with how wide this interval was. What should he do to produce a narrower interval with the same level of confidence? So I want to keep my confidence the same, but I want to reduce the width of the interval. What's the only other thing that affects the width? Sample size. And if I increase sample size, that reduces variability without changing my confidence, doesn't it? So if I want to reduce a more narrower interval with the same level of confidence, I'm going to increase sample size. Okay. All right. So let's talk about what we are going to do to actually run confidence intervals. And this is just a silly mnemonic device that I've used in the past to try to make sure we cover all the steps. I construct fabulous confidence intervals. So the I stands for an intro. AP and College Board want to make sure that you understand what type of inference procedure you are running. So you need some sort of intro to state that. Honestly, if you restate the question asked, that usually answers that question for you, and we'll practice that a little bit more later. Construct. That C goes with conditions. So I is for intro, construct is for conditions. These conditions are the same conditions we talked about in Chapter 7. Okay? Now today we're going to discuss proportions. We're going to run confidence intervals with proportions. Next time we'll run confidence intervals with means. So everything I talk to you about today is going to be proportions. All right, our three formulas. Same three we've been doing. Simple random sample. Got to be there. The 10% condition. Remember, the reason why I'm doing this is to check for independence, and you can write it this way, or population is at least 10 times the sample size. Remember, we want to make sure we didn't take more than 10%, so we can assume independence. And then large counts. Both of these have to be at least 10, so we know the sampling distribution is normal-like. So I construct fabulous confidence intervals. I is the intro. We're just going to restate the question being asked. I'm going to construct a 95% confidence interval to estimate whatever I'm trying to estimate. Construct is for conditions. You're going to check the same three conditions you've been checking. Formula. Fabulous is for formula. So I construct fabulous confidence intervals. Intro, conditions, formula. Now, we've touched on the formula a little bit. Right? We've talked about, okay, if you go to your formula sheet, we have this. But let's actually plug in what values we're using there, okay? And the values we're using are this. I know it's kind of small here, okay? Our statistic is what we're gathering from the sample. That's p hat. Our critical value is the number of standard deviations we are away from the mean. That's z. Remember, z measures the number of standard deviations away from the mean, right? And then the standard deviation or standard error of the statistic. Remember, it's called the standard error if it is using a sample instead of the parameter. There it is right there. And that's the same one we've been using, just notice it has p hats. All of our p's were hats in a confidence interval because when you're calculating a confidence interval, you do not know the true proportion at all. Okay? So we're going to talk about how to find z star in just a second. It's z. They just give it a fancy star when it's in a confidence interval, okay? All right, so intro, you're going to make a statement of I am going to construct whatever it is. Conditions, the three conditions we've been checking, simple random sample, 10%, and then the large counts. Formula, your formula is going to be your statistic plus or minus your critical value, number of standard deviations away from the mean, times the standard deviation. But we're using the standard error because we don't know the true proportion, right? Then conclusion in context. We've already done this. You know what this is? If you go back to our notes from day 1 and you find that statement that we made, though we are blank % confident that the interval from blank to blank captures the true blank, that's it. That statement that we made, here, I'll find it for you right here, is our conclusion. We are blank % confident, however confident we are, that the interval from blank to blank captures the actual value of whatever we're trying to find. And that's how you do a confidence interval. So introduction, a statement of what you're going to do. Conditions, you're checking the three conditions. We already know to check for proportions. Formula, here's the new formula. You're going to have P hat from your sample, you're going to have the sample size, and I'm going to show you in just a second how to find Z star. And then your conclusion in context using this statement right here. And that's it. Okay. Now, let's talk about how to find Z star. And to do so, you will probably want to have your table A out. So if you want to go grab your table A, okay, and with our table A, we're going to find Z star. Okay, now we already said, okay, well, 68, 95, 99.7, that empirical rule helps us to know how many standard deviations away from the mean if we're looking at the center 68%, or the center 95%, or the center 99.7. And so we know that this is one standard deviation on either side of the mean, right? 68%. So Z would be 1, 95% is 2, and 99.7% is 3. Well, 2 is okay. You could use 2 for 95%, and you could use 1 for 68%. But honestly, these have been rounded to make it nice and neat for us to remember. It's rounded to 2, but let's find the actual number of standard deviations. And let me show you how to do this. So if I'm looking at the middle 95%, okay, that means that if it's a middle 95%, I have 5% that's divided by 2 in each of these tails, right? That means I have 2.5% in this tail and 2.5% in this tail to make it 100% total. Would you agree? Okay. Well, what I want to do is let's find the Z-score on either side here, right? Now this is going to be a negative Z and that's going to be positive Z. And if I know the area to the left, well, the area there would be 0.025, right? If I turn it into a decimal. Couldn't I look that up on this chart? So 0.025, so I'm looking in the center, find the one closest to 0.025, which happens to be right there. And it's a Z-score of negative 1.96. If you do the area to the left of this one, which would be 97.5, you'll find that Z-score is positive 1.96. Now, when we do Z-star, when you look at your formula, remember for a confidence interval, it has the plus or minus in front of the Z-star already. So it's taken into account that one's going to be positive, one's going to be negative. That's already there, okay? So when you talk about what Z-star is, when you calculate it, just give the absolute value, 1.96. So it's pretty close to 2, but the actual true value of Z-star is 1.96, okay? Let's try another one. Let's try 90%. So if I'm looking at the middle 90%, that means I got 10% split in 2. That means there's 5% here. Oops, not 50. 5, 0.05, 0.05. And so I can look up 0.05 and find the Z-score that goes back there, right? So I go to the center of the chart, look for 0.05, or the one closest to it. Okay, now it's right between these two. In fact, it's exactly between those two. So negative 1.64 or negative 1.65, or I could split the difference and say negative 1.645 even, to be even more specific. So Z at 90% is 1.645. Okay. Now the other thing we can do is we can use inverse norm. Do you remember how to find inverse norm? So if you go on your calculator to second vars, and number 3 is inverse norm, not normal CDF, sorry. Second vars, inverse norm, try that again. And what you're going to plug in here is the area in the tail, so I'll just do the one I just did. So 0.05, comma, the mean, okay, well the mean is 0, because that's, right, standard deviation, Z-score at mean is 0, standard deviation is 1. And then I give you essentially what the chart gave you. Okay, so you can either use table A, think about, okay, it's a middle whatever percent, look up what the tail probability in the middle of the chart and find the Z-score that corresponds to that, or you can do inverse norm of that area at tail probability, 0 and 1, and that will give you the Z-score as well. Now remember, you're using the absolute value of that. Okay. All right, I'm going to stop this video here, and in the next video, I'm going to actually do some calculations with